Welcome back to the Home Lab, and I've got a really interesting experiment to show you today. This one goes under the really strange name of the Cheerios Effect. So, as ever, we'll begin with a little bit of a story and the fact that when you're like me and you're a physicist, you see physics all around you. So we were on holiday last year in the camper van with Barry, and even though we were next to a river, we took his little paddling pool with us so he could mess around with the water and that. And I also took a whole load of these little floaty plastic balls and chucked them into his paddling pool so he could practice fishing them out. And what was strange was, when he put them in, I wanted him to fish each one out separately. But if you waited a few moments, they always seemed to clump together. And if they weren't clumping together, they'd clear off to the side of the pool. Now that's very strange. How did they know where each one was, and how did they know to stick together? And that is explained by the Cheerios effect. So here goes for the Cheerios effect. Let's put one in, and then another one, and another one, and oh, there we go. Watch what they do. They seem to move around, and once they get close to each other, oh, that was really quick, they stick together, or they try to stick to the sides of the container. There's three grouping together. There's that one coming in, and this is a very weird effect, and it's going to take rather a lot of explaining. So to explain the Cheerios effect, we need to understand a little bit about objects in liquids, and let's consider two situations. Those are objects that float and objects that sink. So if you can imagine taking an object that floats and submerging it underwater, it displaces a volume of water that has more weight than its own weight, so the buoyant force is bigger, so it floats upwards. One that seems heavier, is actually more dense, that displaces less water than its own weight, so the weight is the larger force, larger than buoyancy, so it sinks. But something's interesting as well, because what happens with objects on the surface? And as you've seen, some objects that would normally sink can actually appear to float on the surface of water as long as they're not pushed underneath it. So there's a third force we need to take into account, and that's the force of surface tension. So let's quickly look at surface tension. So water molecules have very weak bonds between them, have hydrogen bonds between them because they're polar, one end slightly more positive than the other end. And so they stick together in all three directions. But when you look at the surface, a water molecule at the surface can stick to the ones next to it and below it, but not ones above it because there's air there. And the force between the water molecule and the air is much weaker. So what you can imagine is that the molecules on the surface all stick together in a line and create a flat surface that's quite difficult to push through. And it's this force that's the surface tension. But when you put an object into water, you've now got a force between the water and the object. And that force can be such that it pulls the water up the edge of the object, which I think is the case with Cheerios, or in the case of paper clips, it pulls at an angle that's downwards. Now this is quite complex physics about all the forces involved and wetting angles, etc. But the main thing to imagine is that the surface of the water seems to have a certain strength to it. And that's the surface tension, and it's this effect we're going to use to explain the Cheerios effect. So let's first demonstrate the surface tension with an object that is more dense than water, and yet if you don't break the surface, it will float. So there's a paperclip floating on the surface of water, and you might just be able to see that it's pushing the surface down. It's deforming the surface of the water, which has lots of molecules holding tightly together the surface tension. So there's the paperclip just sitting on the surface tension, and you'll notice it's not moving anywhere. It's sort of staying where it is. Let's see if I can add another one, and let's see what happens. So it might take a little bit of time, but there we go. They stick together, and this is not a magnetic effect. This is due to the shape of the surface and the surface tension on the water surface. So I shook the table and one paperclip fell to the bottom, or at least that proves it's more dense. But what I'm going to do now is add a few Cheerios, and I wonder what you think will happen. Look what happens when I put them near the paperclip. Now that wasn't intentional, but at least it did what I expected it to do. That they actually move together, the Cheerios, as we might expect, but they don't want to stick to the paperclip. They actually move away from the paperclip, and they move to the sides of the container, or each other if they can. So without lots of force diagrams and mathematics, let's do a sort of simple hand waving explanation of what happens. And it's actually easier to understand with the paper clips. With paper clips, you can see that the paperclip sort of pushes the meniscus down and creates a dip. So it's not that difficult to appreciate that if another paperclip comes close, it will fall down into the dip of the other one. In fact, they move together. So they're moving to a lower energy state. Now, think about the Cheerios, and I suppose this is the final simple explanation of the Cheerios effect. If two Cheerios get closer together, then if you think of the angle at the side of each one, as they come closer, they have to float. So as one, imagine, comes closer to the other, if it came closer and closer, it couldn't just go under the water. It actually floats up the side of the other one and vice versa, so they stick together. And paper clips will stick together because they've both got dips, and Cheerios will stick together because they've both got a liquid that's moving up their sides. Whereas a paperclip and a Cheerio will actually move apart. So as you've noticed, the water and its surface tension has an interesting effect when you put the Cheerio in or the paperclip. In the case of the Cheerio, which is less dense than water, so it definitely floats, the liquid, the surface tension causes it to move up the side of the Cheerio. Whereas the paperclip, which is more dense than water and therefore should sink, doesn't quite push through the surface tension of the water, but creates a dip. And I thought long and hard about how to try and explain this with a little bit of apparatus, and last night I thought, I've suddenly got a reasonably good model to show you. So what I've got here is a rigid bar, a pencil and two springs. Imagine this spring is the paperclip and this spring is the Cheerio. So when we put them in the water, the paperclip is trying to sink, so it's pulling the surface of the water downwards, but hopefully not breaking the surface tension. The force isn't big enough. Whereas in the case of the Cheerio is trying to float as much as it can, so it's actually lifting the liquid surface up. So you get the liquid moving up the side of the Cheerio and producing a dip with the paperclip that wants to sink. So why the Cheerios effect, you might ask? Well, I think the reason for that is that when you put Cheerios on the surface of the water, you notice the bubbles do similar things, by the way. They move very, very rapidly. You see the effect happen quite quickly. And so, unlike objects that are a bit denser, Cheerios, because they're sort of so light for their size, move really rapidly. So a small force on a very small mass will cause it to accelerate. But if the mass is very, very low, the acceleration will be larger. So they kind of get up to speed quicker. So instead of being a process that happens very slowly, as soon as you have your breakfast and put your Cheerios in the milk, you see them move and speed up. And so it's an effect you can easily see when you're having your breakfast. So just before we go, I thought this was too good to miss. So I'm going to put the paper clip back on the surface of the water. And hopefully it won't break the surface tension. And then what I'm going to do is add just 1 drop of washing up liquid, and let's see what happens. There we go. It's fallen straight through. Now you might think I disturbed the surface there, but what in fact I did was change the nature of the surface of the water, and that has the effect of massively reducing the surface tension, and the paperclip just falls straight through the surface. Without wanting to get into a long story, I remember my father, when I was a child, telling me stories about when he was in Africa as a doctor, and they used to put a thin layer of oil or petrol on some of the bits of the lake, and they hoped that the mosquitoes would fall through the surface and that would reduce the risk of malaria. So I do hope you enjoyed that video and you put up with what was really a bit of a hand-waving explanation. There's some quite complex physics and mathematics behind this, but have a play and you get the general idea. So I'll be making another video soon, and I look forward to seeing you then.